Hi all, myself Krishna, and I take care of the BMS application. It's like more of like algorithm development for the BMS, and today on this like bootcamp we will be discussing about the powertrain simulations. So I'll be like briefly touching out the equations, like how we can model them. Yeah, I won't be like teaching much on, or like won't be discussing much on the equations. So we will like focus more on the results, and like more of, instead of like more on results, like we can say like why these models has to be built, and from these models what we can get. And so once we have some set of like information, and from these information which we get from the models, okay, these information how it like gives the direction for the development, right? So in that perspective we will try to put some comments. Okay. Yep. So in the meanwhile, if you have any like queries, or like if any some small expectations on this topic, you can just put out in the comment box. We can plan to take at the end of the session. Okay. Yeah. So here, just a brief agenda. We'll just try to look into the some forces acting on the vehicle, and the travel and dynamics, and some approaches. So why two approaches? Why don't we stick with the only single approach? Like why we need to go with like double approach? That means like two approaches. Like what is the need of these approaches? Okay. And at the end, like model estimations, like at the last. Yep. So when we say the powertrain, right? So in the conventional vehicles, our source of the power is your like fuel, right? Like in the fuel is going to into the IC engine and burns and get, and we used to get the power to the transmission and differential. We used to like send it to the wheel, so the wheel will start rotating and the vehicle moves, right? So this is like the powertrain of your IC engine. Okay, if you skip this part, right? The IC engine, where the source of the power. So this we call it as drive line, drive train. Okay. Yeah. So similarly, uh, in your let's say like if I take EV, okay. So it will be something like this. Okay, I'll just show you and I'll come back to this part. Yeah. So in our case, like this will be the source, and this will be our drivetrain. Okay. Yeah. So yeah, this should be like considered as a powertrain. Okay. Yeah. So we'll just discuss. So like so here in the while we are discussing at the agenda, we got to know that the two approaches, like one with the I'll just show it here, like Quasi-Static approach, and one more with the dynamic approach. Okay. So what are the end goals of this modeling, right? So on the one side, we can say that uh, we can start sizing our components. So what are the components? Let's say, like if I take, okay, in my context here, I will be talking only on the EVs. So if I take EV, so what are the components in it? Like, let's say when we talk about the powertrain, right? So your motor will be your component, and controlling your motor controller, it's also a type of component. Okay. And then a battery. Yeah, so all these are like components which are like uh, a kind of like source producer and source carrier to your wheel, right? So like how to decide like what kind of motor we want, what kind of battery we want, like what power of the motor or the what or like energy of the battery we need, right? So we need to make a decisions. So how we can do it, right? So here like we can say that with these models we can start estimating or like calculating that like what is like how much the power is required. Okay, let's say like you have one vehicle. I'm just trying it in the form of box. Okay, so if I want to like let's say like box itself, if I want to move this box, so I need to know like how much power I need to like apply so that the box moves in this direction. So what is restricting the box to move? So there might be whether it might be placed on the surface. So there will be some resistance from the surface. Okay, and if box is something like uh, having like higher area, so it might be get influenced by aerodynamic force, something like that. Okay, so these all like causes a resistance, so we need to overcome, right? So similarly, in order to overcome that, like we should calculate how much power is required. So in the same way, like we will be applying the same concept like what I showed here, like to the vehicle. So you take a bike, you take a car, you take a truck, anything. So we will be like estimating that what is required in order to move an object. So and what all resistance is like a resistive forces which is like giving a resistance for the movement of the vehicle, so that we will calculate, and then based on that we will start like uh, designing our requirements. Okay, so let's say like, so if this is the vehicle and we are like applying uh, there is some like frictional rolling resistance you can say, okay, due to the friction and aerodynamic force and the gradient that is like against the gravity at some particular angle. Okay, yeah. So because of this you will be like wall will be acting as a resistance. Okay, and you have to overcome this resistance and then you have to move ahead. So with this you can get to know like what is the power required, so force required, total force. Okay, so that I will come here and just show you. Yeah. So I'll just come to these parts just. So we will be calculating the total force. So and then from the force we will be like going that like torque and then power. So based on some our equations, mechanical equations. Okay, so from this we can get to know what could be the power of the battery, power of the motor, such. Okay, so we will discuss those points quickly. Uh, just so we'll just see like how these let me show you how these resistance, like I said that like there are like three resistance like rolling, aerodynamics and gradient. So how these are like affecting to the vehicle. So you can see this pie chart, like what resistance are giving, like how much they are contributing. Okay. And the resistive forces with respect to the speed. As the speed increases, what all resistance are getting influenced and how they are like contributing. Okay. Yeah. So we'll try to like look into each. So when you take a wheel, right? So what all the properties are contributing on the rolling resistance? So you take the tire pressure. I'll just try to take some points here. Like you take the tire pressure and even the material, okay, which I'm going to be discussed in the next. And here the important is like contact patch. So if uh, the width of the wire is sorry, the width of the tire is like higher, so more contact patch. So more contact patch, like more friction force. So yeah, like designing our tire also matters a lot. And even the like you can see here the tire pressure and the velocity, how it is affecting. You can see this constant value, like coefficient of the rolling resistance, how it is getting influenced as the speed increases and as the at the different tire pressure. Yep. So and even the, yeah, this is with respect to the road surface. So how the surface is that, based on that and with respect to the vehicles, you can get the CRR value. And even the CRR values is getting influenced by the temperature. Yep. And then the material, as I was talking earlier, like how the material at the different pressure, it is contributing the like resistance. Yep. So just a second. Coefficient of rolling resistance, CRR means. Yeah, this recording will be shared. Okay. So we understood like what are the influencing factors for the rolling resistance. Like we just saw that um, like the material of the tire, the design of the tire, the surface and the tire and the temperature. Okay. So like considering all this, like there is some constant term is generally represented like it has like CRR, that coefficient of rolling resistance. So this is a generic equation. Okay. So if you want to define it more precisely with respect to with considering the tire pressure and the velocity, so there is one more equation here. Okay. Yeah, where it can you can say it as like dynamic CRR. Yes. Yeah. And you can like there might be like some more uh, rolling force resistance estimator equation. So it might include some more components in it, such as like tire pressure, velocity. Okay. So the now like aerodynamic force. So aerodynamic force, it is given by equation like 0.5 rho. A is area of front front of your vehicle, and CD is the coefficient of drag, and V square is the velocity. Okay, it's just a square root of the velocity. Yep. So here, if you see that the first equation, yeah, I think like the font has been changed, maybe because of the change of the application where I am open. Okay, I hope it's fine. Yeah. So the aerodynamic force, the equation which you are seeing here, that 0.5 rho a c d v square, you can consider it as a generic form. And again, like there are some different forms of the aerodynamic force equation. That is, if you're against the wind and the wind is along with you, based on that your wind velocity can be added or subtracted. Okay, so but generally for our estimations we will stick with the first one. And how this drag, it depends. So we might have studied that like different shapes contribute the different drag coefficient. So if you see all these shapes, somewhere our automotive industry may lie over in this area, like the last one, streamlined body or half streamlined body. Like even the planes, rockets are like in this shape, streamlined body or like streamlined half body, so that we get the low drag. Yeah. And how this velocity is influencing the aerodynamic force. So as the velocity increases, the aerodynamic force is also increases. So because you can see the equation, they are like directly proportional. Here it is like directly proportional. Sorry. Let me write it clearly. Yep. So it is directly proportional to the rho, area, CD, and V square. So if any changes in these values will affect your aerodynamic force. Yep. So then the air density, like at the different temperature, we can see the difference in air density. Okay. So we know that the change in density also influence the force. Yeah. And these are the same equations which I wrote in the earlier slide. Now we'll discuss about the gradient force. So this is like one of the force that where there is an inclination, like you need to put more effort uh, to overcome that inclination. Okay, this is something in the standard. Like I will just check it later. We'll check it later. Yeah. So the gradient force, like it is denoted with like plus or minus GVM into sine theta. Okay. So the equation we can see over here, right? Why the plus or minus? So it is because of like whether it is an downhill or like uphill condition. Is it a downhill or uphill condition? So that defines your like plus or minus. So if it is a downhill, we will not consider the gradient force. If it is uphill, like we have to consider the gradient force. Yeah. So then there is something called acceleration. Like I'll just tell a story for this one, like how we can understand this one. Yeah. So here we discussed about like rolling resistance, gradient. Sorry. Yeah, this part. Aerodynamic force, rolling resistance, and gradient, right? And then there is something called acceleration force. We know that how these three are influenced and how they are contributing to your vehicle motion. Okay, these acts as a resistance. But what about this one? So just take up some kind of box which is placed on some surface. Okay. So if I put a force from this direction, let's say like F, whether this box moves or not, will we will not talk about it, but just say that we have applied the force, and this is where we have placed like on the surface of the on some surface the box is placed. So here we can say that some resistance is there due to friction. Okay, I'll just write FR, something like that. And the box might be having some good area, so it getting influenced by aerodynamic force. Yep. And this surface is having no inclination, so let's like not consider the gradient at all. Okay, so let's say like the resistance, friction force, or like aerodynamic force, let's say like this is something the value is 30, and this something the value is the friction resistance is something like 10. So the total force which is in the form of resistance is like 40 Newton. So if I apply the force in this direction, let's say like if I apply 40 Newton, so the box still moves or not? Like it doesn't move, because now it reached in like balanced mode or equilibrium. Okay, yeah. Now if I start applying some extra, let's say like 41. Okay, I'll just write it over here. So it will move in this direction where I'm marking. Uh, but at what velocity it's moving, right? So it might be like very minimal velocity. So if I make it like 141 Newton, then it may move in this this box may move in this direction at some good amount of velocity, right? So that is how this acceleration force acts over here. So whatever you are putting the force here, right, this is nothing but your acceleration force. So including this, you need to consider along with these resistance forces to come up with the total tractive force. Yeah. So once you have this total tractive force, you can like go for calculating the torque. Okay. Torque is nothing but your Newton meter. From the torque, you will be having the equations. So I'll just go to those part. Yeah. Let's say like this is just a drivetrain transmission modeling. So let's say like torque. So if you have the torque, so you can like calculate the torque with the help of like equation called 2 pi nt upon 60. So this is your torque, this is your speed. So speed we get through wheels. From wheel with the transmission help, we can get the motor speed. Okay, 2 pi nt upon 60, we can get the power, which is in watts. Yeah. So this is like we are calculating the power which is at the output end of your motor. So I think might be here. And on the other hand, like like motor will be having some efficiency, right? So whatever the input power we give, it doesn't give like complete like if we send like 100 watt or something, we won't get like exact 100 watt as output, right? There will be some losses. So now here we have estimated the output power, right? So now with including the efficiency, we have to calculate the input. So there is some mapping, there will be some maps, okay, at the different speed and the different torques, what is the efficiency. So yeah, so with that you will calculating the motor power input, and from the input like you can consider the efficiency of the motor controller, and you can also include the efficiency of motor controller, and you will be getting the battery output power. So from this battery output power, you can like calculate the battery energy, and from there the many parameters such as like current, voltage, okay, and like what is battery energy required for these kilometers to run the vehicle in these kilometers, number of cells in battery, parallel or like cells in series and parallel, and capacity of the cell, C rates. Yeah. So all these can be like estimated. Okay. So yeah, these are the same like terms which I used: battery current, range, battery current, the C rates, and yeah, you can like put up the SOC equation to calculate the SOC of the battery. So we got to know like what all the terms here we are like dealing, right? As we, okay, I'll just, yeah. So before going into the models, I'll just try to put some points over here. So as we see that, uh, like when I was mentioning that models, right? So there we were dealing like component sizing. So with these estimations, we will be calculating the power requirement for your motor, like because if you know what force is required at the wheel side of your vehicle, so in order to overcome that force, you can calculate the power. So with once you know the power, so based on that, motor selection can be done. So what should be the speed of your motor, what should be the power of the motor, right? And what kind of motor controller for it. Similarly, the battery, right? So in order to drive that, in order to like drive that motor, okay, so how much power it has to be supplied, that's matter. So that is how it lead us to the battery sizing, right? So if I'm getting some C current, some C rates, some current value, so with those values we can go up for selecting the selection of the cell. Okay, let's say like we have to operate our cells in 2C rate itself in order to meet our requirements. Then in that case, then we have to like search the cells which can give continuously 2C rates. Yeah. So yeah, this is just giving some brief ideas like how we can, how these results can help us in making this decisions for a like battery development also. So yeah, so currents, so you can get to know like what current is required. So with these currents calculation, which also help to like size your wires, right? We know that like a lot of wires are there for the low voltage systems and for the high voltage systems, right? And if we know like how much current is flowing in where, then we can also size the wires. Yeah. So in this way, we can use these models for making decisions. And yeah, so this is about like how you can make use of the outcomes. So uh, even like it will lead some, as you get the current profile from your vehicles, you can just feed up your BMS models, okay, like SOX estimations, so that you can like calculate your SOX, that is, it might be SOC, SOH, or anything. So in this way, it will also help in the further decisions. Yep. So I'll just quickly go to the models. So here, this is something, a powertrain model. This is the quadratic approach. On the other hand, I have like forward approach. The equations are similar. Only some part is extra in the dynamic, that is um driver model. Okay. Yeah. I'll just explain like why it is there. So here, like whatever the equations we went through, right? The same thing I have like put up in each subsystems. Okay. And here I will be feeding my drive cycles. Based on that, I will be getting my results. Yeah, these are like developed by us itself. So we are just using some empirical equations uh, through the papers, publications, and based on that, we developed these uh, yeah, models. These are not ready-made available from the MathWorks. Yeah, but the equations might be pretty same. Like we might have included like some more influencing parameters, or like they might have included more influencing parameters. It depends. Yeah. So this is box where we can collect the vehicle body, and like where we will designing our like resistive forces and estimation of your wheel torque, wheel speed. From there, motor torque, motor speed, and then battery power, battery. From this battery, we can like calculate how much energy is required, all the stuff. See, no, number of series in number of cells in battery, which number of cells in series and number of cells in parallel. Yeah. So these are some results. If I take the wheel torque, these are some results. So this, the second graph is about motor torque. So we can see that how much like what should be my nominal torque of the motor, what is my max torque of the motor, right, from this graph. So nominal means like you can say a rated, like which is continuously required. um, so we can't make a decision of the torque or the speed or the power from a single drive cycle. We have to feed some good amount of drive cycles. Let's say if you are defining your vehicle, or if you are like developing a vehicle for this, like let's say like for the within a city, for the urban application. Okay. So yeah, not for the long drive. Okay, EVs are like right now in the market, EVs are not uh, appreciated for the long drive still. Okay. So yeah, because of not giving proper mileage. Yeah, we know that. So let's say like considering the urban conditions, like city condition, so we need to like have good amount of velocity profiles of the cities. So we have to feed and get these data, and based on these data we can like start making the decisions. Like if you want to go for continuous torque requirement, you can like put some histogram graphs from the results. Like we can see that which value is continuously repeated, so that we can consider as a continuous torque, okay, requirement. And let's say if you are like want to define your acceleration part for your vehicle, okay, because usually when you want to develop a vehicle and sell, you need to mention that like at this particular at this seconds, like you will be able to reach this speed, right? For example, like I'm just taking a random number, like 60 in 3 seconds, right? 60 kilometer per hour in 3 seconds. So you should be knowing, like in order to reach that 60, so what should be my peak torque, so that you can define from the results. So similarly, if I see the motor power also, yeah, you can calculate what should be the wattage of your motor, and the battery current, C rates, and further you can like calculate the battery power, battery power, battery voltage by using the Ohm's law itself, like P is equal to V into I. Yeah. So these are like pretty straightforward results, and this is one of the other model that we can call it as like dynamic approach. So the rest part, like most of the part, it has like same equations, everything is same except this subsystem, that where your uh, driver model, we just introducing the driver model with help of PID controller. Yeah. So what exactly we are doing in this model, right? So here we see that we are feeding one drive cycle. We call it as a reference speed. So here we are feeding as a reference speed as a feedback from your at the end of your model, right? We are getting some velocity term here. We call it as actual velocity. Okay. So what exactly the physics behind this model, right? So we are feeding a reference speed in order to like achieve this speed. So if I open this graph, so you can see that uh, let me show you. Yeah. So this is some speed value, and this is the top speed, and you can see the graph is suddenly increasing, right? Okay. Yeah. So it might be like went from 0 to 50 within maybe like 5 seconds. We don't know, like we don't know that time. I'm just trying to put. So in order to like happen, right? So how much power is required? How much torque is required? Okay, in order to achieve this speed, what should be my motor speed? What should be my motor power, right? So this velocity profile is already having the acceleration, uh, the speed data, the speed information, the rest, and everything, right? So in order to like achieve that speed profile, like how much we need to supply the power, that we are going to do it over here. Okay, right now you can see here, uh, right now like it is not exactly matching at this point. So for example, so my actual speed, so this is gain is nothing but your let's say your reference speed. I'll just try to rerun this one so that your map will get updated. Yeah. So the reference speed and the actual speed. So yellow is the reference speed. So that is your actual, sorry, that is your like true value. Actual speed is a produced value. Okay. Yeah. So I have in the model, I have already defined some torque and the power somewhere in this model. Okay. I'll will try to like do some changes and we can see how the graph works. So right now, if you are like I have put some value and this is how my actual speed is behaving. So up to this velocity, I'm like able to like exactly overlap on the reference speed. As it goes at this velocity, you can see it is not able to like exactly overlap. Okay. Or you can see, yeah, if I see this part, so it is like delaying, it is taking a lot of time to reach this point and similarly at this point. Okay. Yeah. So let me, okay, let me cancel this graph. So now like I'm feeding some value over here. Like let me make it like 25,000. Like it can be like 25 kilowatt. Yeah. And I'll rerun this one. So now you can see like it is exactly overlapping. So I just increase the power. Okay, let me decrease it by 5, 5K. So again, let me check the results. It's still pretty giving good results. Let again decrease by 5K. Yeah, now you can see some changes at this point, but still up to here, it's giving good. I'm just based on some visualization I'm telling. Okay. Yeah, it might be like I can see some small changes. If I zoom it, we can get to know, but it's okay, negligible. So here we can see like considerable changes. Yeah. So like yeah, based on these like we can like make the decisions, right? How well we are satisfying the reference velocity profile with changing the torque stuff. I'll just change the torque of my uh, supply, the torque supply. I'll just make it 50 something. We'll see like, okay, it's pretty much good. I'll make 30 Newton meter. Yeah, we are started seeing the changes. So this is how we can like set up the values and we can make the changes. And we can see how well we are satisfying the reference speed. And based on that, we can derive our like how much torque of the motor, how much power of the motor we need to consider. Yeah. So yes, so like I hope this bootcamp give you some idea like how we can make use of like the outcomes of these models to make the decision of your component selection, sizing of the components. Okay, so thank you.